Okay, I hope I'm live, or I thought I was live, but I wasn't. So I had to figure out everything. Um, I don't know which screen is visible to you guys. Okay, so basically, what I'm doing, why I'm doing, um, I am just doing it to to just learn. There's no purpose, nothing. So yeah, that's my whole thought process at this point of time. And what page it is? So yeah, let me open uh, my OneDrive first. OneDrive, no, OneNote first, and let me describe you what I'm doing, what's my plan, and I hope it's visible. Okay, why I think the screen got stuck at the page, at the Safari page. I don't know why it's happening, but I even closed that page, so yeah, it doesn't make any sense. Yeah, it's visible. All right, I can just uh, read the things now. So yeah, what's the plan for today? And overall plan, we will discuss everything. So yeah, this is the overall structure that I want to follow, which is first I will jump into multivariable calculus, in which I will be reading about vectors, matrices, and planes, 3D, you can see. And after that, I will jump to probability and stats. So in probability and stats, this is the core thing that I want to study, and again linear algebra, and then maths with application in finance. um, Basically, I'm preparing for quant, so these are things which will help me in one way or another. So yeah, I'll be reading those kind of stuff, and after that we'll learn a single variable calculus and multivariable calculus. So this is the thing that I want to implement, study, whatever you can say. um, so okay, also along with this, I will uh, learn, read, whatever you can say, in two slots or maybe in three slots. So in one slot I will be doing only maths, and in one slot I will be doing CS, uh, maybe core subject of CS, maybe kind of uh, applied quant CS. Okay, and in the last slot I will be um, okay, I will just show you guys what I'm about to do. So this is a to-do list that I want to do today. Okay, yesterday I did stream and I did quite a few things. So what I did was I, uh, I started with multivariable calculus and I finished 4 sessions of vectors. So vectors are here divided into 3 and 4 sessions, 3 and 4 parts. Three, yeah, I guess 3 parts. And for in part A, there are 8 sessions, and I did 4 yesterday. So today, this is the another slot that I'm talking about. I was talking about. So this is for mainly CS. So I'll start with math for CS. I will do this and this both. Why? Okay, there's a question that there's a debatable question, I would say, that why I'm even doing math again if I'm doing this here. So this is very quick maths kind of thing, like yeah, you all can understand. um, like for CS, this math is specifically for CS. So in this course, it will be just, we will just skim through the maths, we will not learn the underlying deep concepts, but we'll be covering things in a basic manner, applicative manner that we can apply in CS. So we will try to do this quickly, and we will build our depth, build our grasp over it, uh, from these things. Okay, and after that I will go to Python, DSA, and then graph is important for me. uh, yeah, and also we will do the core CS things, but I have to finish till uh, here, and this all probably around August, September, which is doable, but I'm not sure. And also, uh, I figured out there's a poker theory course at MIT, so I will be doing that on. But whenever I do get bored or something, I will do that. There are a lot of things to do, but I want to do everything sequentially and in a way so that I don't mess up things, and I will just uh, do one or two things at a time at max. So yeah, that's what I'm planning to do. So should we just start with what? Let me see. So what's in to-do list? So to-do list, we have to finish at least one unit for maths, maths for CS. Okay, and then I did 4 sessions of vectors yesterday. um, I have to revise that, and also there was some underlying trigono concepts that I want to revise. um, and yeah, we have to finish 4 more sessions of part A vectors. Okay, okay, it's doable, it's doable. Let's do this. Hopefully I'm opening right browser. Yeah, so here we are. uh, we have to study maths for CS now. Okay, I will just open it and bring it back. I read maths for CS first part, so it was more of a theory heavy section. So hopefully we'll do it quickly. um yeah, so here it is. uh first first unit starts with proof, and yeah, it was 11. Yeah, okay, let's start. Let me go to resource index, and we can start from there. So what is my process is, first we will do lecture, then we will just skim through the reading and whatever examples or the things that that got that was explained in the lecture. We'll just take a look on it quickly and then move on. So yeah, let's go to into the proofs. Okay, let's read it. What's this? And I have to actually check uh, if my stream is okay or not, because I don't want to lose onto the memory of my first stream that, yeah, it's, I thought it was streaming but it wasn't, so that would be a bad thing. let, let me give me a moment. Let me give me a moment. Yeah, To just learn. There's no purpose to the proofs. There's no purpose. All right. I guess all good. So we can just go ahead with whatever we were doing. And yeah, let's read first. I have to zoom it a bit. Okay. Okay, I will try to speak not much, just read, and if I get something uh, in my thoughts or anything, I will speak and write it down. Okay. So first thing is really simple. What is proposition? So propositions are statements which are either true or false. uh, this is true, this is false, so both are propositions. Okay. Okay, so here's a theorem. uh, for every non-negative integer n, the value of n square plus n plus 41 is prime. uh, should we take an example and check it? Like, yeah, we can do this. It seems fun. Okay, this is the rough. This is where I do rough works. So yeah, we just have to take this into account that uh, that and let's start with some small numbers, n square plus n plus 41. So this should be prime. So let's take 2 as an example. So 4 plus 2 plus 41, so it would be 47, which is prime. Yeah, it's correct. But if we take like some bigger number, let's say um let's say 20. let, let's take 21. Let's take 21. So 21 into 21, it's 441. 441 plus 21, plus 21 plus 41. So 62. 441 plus 62, 1 plus 62, it will be 503. And 503 is, it's a prime. Yeah, I believe it's a prime. 5, 6, 7, 8. Yeah, I think it's a prime. The theorem is working pretty good. But that was not the question. I just did it for fun. Okay, it looks good so far. Can we just move ahead? Okay, is it factorial sign? No, it's not factorial sign. When we begin with p0 equals to 41, which so yeah, every time when we put a number, it is throwing out output as a prime. In fact, we can keep checking through n equals 39, which confirms that yeah, it's prime. But okay, so in case of 40, uh, it is throwing out 41 into 41. 41 into 41, is it not prime? Uh, 16, I'm not sure. So we will just check. So 40 into 40, uh, it will be 1600. 1600 plus 81. So 1681 is not prime. I'm not sure. 1681. Can we divide it with 7? Nope. Uh, Maybe with 40. Not with 3. Probably not with 3. So not with. So with which number we can divide it? We can divide it by 41. Okay, so yeah, I just messed up. So 41 into 41 is 1681. So we can divide it with 41. So it's not prime. Yeah, makes sense. So what's the conclusion? So it's not true that the expression is prime for all non-negative integers. In fact, it's not hard to show that no polynomial with integer coefficients can map all non-negative into prime numbers unless it's constant. See problem 1.17. 1.17 should be far. Okay, we will see that. But the real point of this example is to show that in general you can check a claim about infinite set by checking a finite set of elements, no matter how large finite set gets. So this is really interesting thing, and I will just note it down. I will create a page. Okay, not with multivariable. I will make a section. Uh, CS math for CS, and I will make a page proofs, and here we can write everything, I believe. So yeah, what we can write is what we got to learn. um, okay, we can claim bro, I want a bigger screen to write it. I can write it on my second screen, but then I can just live stream it. So uh, it's pain, it's actually pain. Okay, never mind. I tried to change the settings a bit, but we have to go with it. Okay, we can claim about infinite sets, I believe. That was hidden. It's really small. Okay, let me first fix this. After that, we will uh, do everything in sequential way. Okay, so 75% zoom looks okay to me. I don't know how people do it. Like I can read in one a screen, write in one screen, but it's complicated. Um, I think I should keep this screen here only, and this in which I am reading, I will just read and drop it in my second screen. So that's what I can do. Okay, so I will do that. I will keep uh, one note constant in one screen. I will just move around this browser screen. Okay, this seems this seems optimal to me. So okay, yeah, I'm doing it really slow. I need to speed up. So we can claim about uh, an infinite set. Uh, okay, I can do one thing. I will try to keep it by checking finite sets. So yeah, we came to this conclusion, and hopefully I will be quick afterwards. Okay, what's next? So so by the way, propositions like this about all numbers, all terms of some kind of are so common that there is special notation for them. This notation proposition would be Okay, for all number, this is the sample for all number. Okay, we all know that. This is belongs to, and it's natural number. So Pn is prime. Okay, here's sample for all the sample and stands for a set of non-negative integers. Ask your instructor for complete list. What? Ask your instructor for complete list. Okay, it was a pun, not fun. It was a pun. The sample A leads to is member of, yeah, it belongs to, or simple. It is n. The period after n is just a separator between the phrases. Okay, so this dot is basically a separator. So yeah, it's just basic terms. So Euler's conjecture. This is the equation. Uh, a to the power 4 plus b to the power 4 plus c to the power 4. So this will be d to the power 4. So has no solution. A, B, C, D uh, are positive. Okay, Euler. It's not Euler. It's pronounced as Euler. Euler. Okay, I will just pronounce it Euler. I pronounce it my whole life uh, Euler, but yeah, today I got to know the real pronunciation. Okay, we can move to the next thing. So okay, he conjectured this in 1769, but the proposition was to prove false. Okay, it got proved false after 218 years by Noam Elkis at a liberal arts school of Mass Ave. The solution he found was A equal to this, B equal to this, C equal to this, D equal to this. Um, okay, in logical notation, Euler's conjecture would be written as, so this is positive integers, z plus all of positive integers. Uh, so all of A belongs to positive integers, all of B belongs to positive, all of C belongs to positive, all of D belongs to positive. And if we into this term, then it won't be equal to d to the power 4. Okay, should we just check it once? um, we can actually. Let's do this. uh, okay, let's do this. Let me create a rough page here too. Can I put it above this? Probably, yeah. So let me name it as rough. um what was the what were the terms? Let me write it first, then we can just check it by calculating everything. I believe we can do this. So let's say um, a equals to 95800, b equals to this, and c equals to 41460, d equals to 31. So in this is Euler's conjecture. This should be equals to this. Everything here uh, belongs to positive non-integers, non-negative integers. Yeah, so positive integers. Okay, so if we take root 4 of everything, wait a minute. Okay, so what we have to do here is we have to take 4 times of these numbers. Okay, I calculated it and it came out to be very large number. So can we can I bring my calculator here? Okay, I wondered how they calculate all of these without calculator. Okay, one more interesting thing that I realized, there should be a lot of conjectures or theories which got proven wrong because uh, because of the same thing. They got they got claimed in a finite set instead of like figuring out in infinite set. So let's say for this thing, so if I use the calculator, so the number is 95800. So it would be to the power 4 and it would be a very big number. So can we just add 21719 to the power 4 and 4145560, this 2 to the power 4 and no, this only. Now what was the conjecture? Yeah, this only. So whatever is this term, it should be equals to 4 times this. No, not 4 times uh, power of 4 this. Okay, I will just okay, it comes out to, yeah, it's really big large number. So this is our, can we do one more? I have to bring out one more calculator so that we can just cross check. So the number is 422481. So here I calculated this number too. So are they equal? um are they equal? They were very close actually. So 10 to the power 22, it's probably same. um where's the difference after this? So this is only a difference. What's the value of e? Can we check? value of E. Yeah, in maths, physics, whatever. It's Euler's number 2.17. 2.17. So yeah, it's different. Bro, it was really complicated, and whoever proved this. Okay, we got that. There was a very minute difference, uh, and it was actually an interesting one. So yeah, we can move on to the next thing. So this has no solution when this equals to this belongs to positive integers. This proportion also false, but the smallest count example has more than 1,000 digits. It's worth mentioning couple of further famous proposition whose proofs were sought for centuries before finally being discovered. So basically, these uh, conjectures or propositions, I would say, uh, they were proved first got claimed or verified in a very finite set because there wasn't uh, uh, calculate there weren't calculators, but when calculators got invented, then we can use it and run on finite infinite sets, not infinite but on a very bigger amount of sets. So there was room to improve the conjectures or even make a false proposition on the conjectures give which was which holds their value. So a lot of conjectures after inventing calculator um, turned around. Yeah, it's it's a good thing that we got to learn. So four color theorem for every map can be colored with four colors, so that adjacent region have different colors. Different. Okay, so it is basically a interesting thing. So four color theorem. So every map can be colored with four colors, and and then every adjacent region can have different colors, but the boundaries should meet uh, in a positive length, not only at a few points. So okay, yeah. So basically, with proofs, into the proofs, we just got to know that the propositions can be true and false in one term and another. We can just judge a infinite set by just sampling out and making assumptions on a finite set. So yeah, and that's what we got to learn so far. So I will just quickly read this, and if there is anything else we will cover it. So so this is interesting because it holds its value till date, and for up to this number it's true. So every even integer greater than 2 is the sum of the two primes. Let's take 4 as an example. So yeah, 4 is a addition of two primes, yeah, 1 and 3. Yeah, can we move ahead? So what I feel like, this same thing is happening, this same thing happened with algorithms before, and at this point of time this same thing is happening with LLM models. So we are kind of uh, circulating in a loop, but with advancements. But the whole concept, whole baseline, it's actually same. Okay, I will write this thing too, because I feel like it's an interesting thought process. Can I change the ink? Okay, so Okay, we can move ahead now. Predicates. What's that? A predicate can be understood as a proposition whose truth depends on the value of one or more variables. So, n is a perfect square. Describe a predicate since you can't say it's true or false until you know the value of a variable n happens to be. So, yeah, n is a perfect square, we can say till we get a number. So, let's say we have 3. It's not a perfect square. Let's say we have 25. It's a perfect square. Okay. Okay. So, what's the notation here? Like other propositions, predicates are often named with a letter. Furthermore, a function like notation is used to denote a predicate supplied with specific variable values. For example, we might use the name p for predicate a verb. Okay, so and repeat the remarks above by asserting p is this true, p is this false. Okay, notation for predicates is confusing similar to ordinary function notation. P is predicate, then Pn is either true or false depending on the value of n. On the other hand, smaller p is an ordinary function like n square plus 1. Ps is numerical quantity. Okay, I got it. So the capital P is for predicate, and for smaller p it is for ordinary function where after like solving or defining the equation or function we can we came to conclusion that the p is numerical quantity. The axiomatic method, the standard procedure for establishing truth in mathematics, was invented by Euler's knee. It's Euclid, a mathematician working in Alexandria, Egypt around 300 BC. His idea was to begin with 5 assumptions about geometry which seem undeniable based on direct experience. For example, there is a straight line segment between every pair of points. Um, okay, yeah, it's true. Is it true? Okay, I have to actually figure out is it even true or not. So, wait. So, important true propositions are called theorems. Okay, so yeah, it is theorems. The true propositions are theorem. A lemma is a preliminary proposition useful for proving later propositions. Okay, uh, what's that? A corollary is a proposition that follows in just a few logical steps from a theorem. Our axioms, the ZFC axiom, are important in studying and justifying foundation of mathematics, but practical purposes they are too primitive. Proving theorems is ZFX is a little like writing programs in bytecode instead of full of fledged programming. Yeah, okay. A formal proof in ZFC that 2 plus 2 equals to 4 requires 20,000 steps. Okay, so instead with starting with ZFC. Okay, so what is ZFC? Oh, it is ZFC. this will give us a quick launch, but humify imprecise specification of axioms troubling at times. For example, in the midst of the proof, you may start to wonder, must I prove this little fact? Um, or can I take it as an axiom? There really is no absolute answer, since what's reasonable to assume and what requires proof depends on the circumstances and the audience. A good general guidelines is to simply put up the front about what you're assuming. Okay. Logical or deductions. Logical deduction or inference rules are used to prove new propositions using previously proved ones. Okay. Fundamental interface. So basically, it's a inference rule that we can follow. Uh, so through this, we can prove everything that could be true or false. Okay, this was very exhaustive material, I would say, because I didn't feel felt like felt like that it would be that exhaustive, but it was. Um, can we read more? Where were we? Yeah, patterns of proof. Okay, this can be interesting. Okay, so every proof have some patterns and some baselines to follow, proving an implication. Propositions from if P then Q are implications. So it is basically the core thing that we learn in like uh, basic algorithms. So this is the same thing that we learn in basic algorithms. Like if this then this. So now we can understand where these kind of terms came from in Python, in any other programming languages. So everything got derived from mathematics. Okay, we can just move ahead now, quickly. Um, okay, so this is the implication that we can do. Yeah, so this thing is implication. If P is happening, if P, then Q, it's kind of like that. So this implication, this is quadratic. Why it is here quadratic? um yeah, so it is here because if this is happening, then it will happen. Okay, it is just implying this thing. And again the Goldbach conjecture. So if n is an even integer greater than 2, then the sum of two primes. Yeah, so if this is happening, then this will happen. Okay, so yeah, this is basically what builds our foundation. This is basically what's the the basic the basic of the basic logic that we can just apply. So here we will just know how we can prove this theorem. Okay, and here are the points which is important. Yeah, so these 2 points are important. So you will often need to do some scratch work while you're trying to figure out logical steps for a proof. Your scratch work can be disorganized as you like, full of dead ends, strange diagrams, obscene words, whatever. But keep your scratch work separate from your final proof, which should be clear and concise. Yeah. Proofs typically begin with the word proof and end with the sort of delimiter like this or QED. The only purpose of the conventions is to clarify where proofs begin and end. Alright. Man, it's not interesting. I mean, okay, I should read it even if it's not interesting, but okay, I'll read it. In logically equivalent to controllatives. Okay, controllatives. So yeah, it's basically saying that we can sometimes it's easy to prove the contrapositive instead of proving the positive. Like let's say, for example, 2 plus 2 equals to 5. So if we can prove 2 plus 2 is not equal to 5, then we also prove that 2 plus 2. um no, I have to take another good example. Okay, let's say 2 plus 2 is not equal to 5. We have to prove this in one way or another. So if we prove 2 plus 2 equals to 4, then it also got proved that 2 plus 2 is not equal to 5. I don't know if I'm making sense or what, but yeah, this should be the this should be the thing. Okay, we can move ahead with this. I will just mark it this section. I will read this section again. Okay, we I mean I got the logic, but I haven't got some base examples that I can work upon. So if R is irrational, then R square is also irrational. So okay, this is the good example. So if we prove contrapositive of this, then we can also prove this thing. Yeah, proving if and only if. Okay, this statements this statement gets used in programming quite a lot, so we should read it. Many mathematical theorems assert that two statements are logically equivalent. That is, one holds if and only if the other does. It's an example that has been known for several years. Two triangles have same sides of length, and if and only if two lengths of a triangle and the angle between those are same. Okay, so two triangles will have same length, uh, if and only if the two side lengths and the angle between those sides are same. Yeah, it makes sense, and we can phrase it as I double f. Okay. So here we can construct the chain of if and only if. How we can construct it? We construct a chain if and only if implications proof P is equivalent to second statement, which is equivalent to the third statement, and so the fourth, so until you reach Q. So we are just yeah, like it's chain. It's basically a chain thing. So if one is correct, if one is true, then we move to second, and if second is true, we move to third, and everything is interlinked. So one can only happen if two is two have proper values of, or two is correct, two is in right direction. Okay. And the standard deviation of a sequence of values, this is 0 if and only if all the values are equal to the mean. For example, standard deviation of test scores is 0 if and only if everyone scored exactly the class average. Yeah, it makes sense. We construct a chain of if and only if implications starting with the statement that standard deviation is 0. Yeah, it makes sense. If there's, let's take a example. If yeah, there was already an example of class marks, we will take that and uh, try to say it in broader way. So let's say we have class marks, and if everything is so, if everyone scored y1 marks and there is no deviation, so let's say understand standard deviation as it is that if there is mean and there is no moment, then we will stay at 0, and if it is not in mean and we have some different values, in positive we move here, in negative we move here, so there is some deviation, and at this point there is no deviation, so that a standard deviation will be 0. So this is my thought process. Okay, it was some basic stuff too. Man, it was tough, honestly. I haven't expected it to be the stuff, but yeah, this is the same thing as. Okay, we will just skim through the transcripts. Can I make it bigger? Okay. So here, whatever I read so far, it's not something new. We can look up the examples or the slides too. Okay, let's look at the slide first. I don't want to watch video. I'm not a video kind of person, so there was in class questions too. We will first see what kind of questions they were. And don't tell me this is the first class. Why the problem set seems on a harder sides? Okay, getting started Pythagorean theorem. Yeah, I read this thing in transcript. A cool proof. Rearrange into uh, A into C, C cross C square, and then and A cross A and A B cross B square. Cross B square. Okay, we will get this. And this is kind of complicated. It's not as simple as this because so basically here are some examples uh, which first this follows the same principle that we got here. First there were some good examples which shows how proofs can be verified, and after that there were some proofs which can be which turns out to be false and with an counterexample. So that's what's happening in this section. Okay, let's go through the problems. The Pythagorean theorem says that if AB are the length of the sides of the right angle and C is the length of the hypotenuse, then this the theorem is so particular from here and that we generally take it for granted. But let's be doesn't call it obvious. So we do have to prove it or what? Okay, so we have to do same thing as this. This we have to do almost same thing here. Okay. Isn't it a complex number? No, it isn't. It isn't. Or it is. Not sure. Let me just verify. Let's see under root. Okay, what I wrote, I just misclicked. Under root 1 squared is complex or not? Yeah, it's a complex number, so it can be this thing. So that's why it's a bogus theorem. Yeah. Okay, we will treat this thing. This is interesting. All of that for proofs that I'm not into proofs. I don't I don't like proofs, but I will just treat it. I like solving numbers, solving maths, solving alphabets. Like I said alphabets because it's all alphabets. He announces his class that he plans to surprise them with a quiz sometime next week. First wonder if the quiz will be on Friday of the next week. The reason that it can't, if Hilberg didn't give the quiz before Friday, then by midnight Thursday they would know the quiz had to be on Friday. Yeah, it's true. And so the quiz wouldn't be surprise anymore. Next, the student wonder where Albert could give the surprise quiz Thursday. They observed that if the quiz wasn't given before Thursday, it would be given on Thursday since they already know it can be given on Friday. But having figured out it wouldn't be surprised if the quiz was on Thursday. Similarly, student reason that a quiz can be on Wednesday, Tuesday, or Monday. Namely, it's impossible for Albert to give a surprise quiz next week. All the students now relax, having concluded that Albert must be bluffing. And since no one expects quiz, that's why when Albert gives it on Tuesday next week, it really is a surprise. What if anything do you think is wrong with students' reasoning? I mean, you can reason it. Uh, the reason for Friday is correct. Um, that if there's no quiz till Thursday midnight, then then there shouldn't be a quiz. Then there will be a quiz on Friday. But if let's say if there's a quiz, but we can reason it like there won't be quiz on Monday, Tuesday, Wednesday, or even Thursday. So this could be false. So there will be a surprise element for Monday, Tuesday, Wednesday, and Thursday. And if there isn't any quiz in those 4 days, then there won't be a surprise element for the fifth day, which is Friday, because by that time students will know. That's what I think. I will come back to this question when I revise it again. From here, maybe things will get interesting. Let's say, let's see if this is interesting or not. I will read these things too. Or I just read this thing too. Wait, wait. Okay, didn't I just read 1.1 to 1.6? 1.5, yeah. Quantifiers and predicate logic. I read this thing, right? Uh, but there were more thing like digital logic, truth tables. Yeah, I have to read this. Let me first go through this. What's this? How sets are um okay, so this is this basic set theory. This seems quite easy as compared to this. I don't know why, but it just feels like I don't know why I feel proofs are proofs are hard. So I never want to be a theoretical mathematician or theoretical. Um, I don't want to get into the theoretical term. I want application kind of things. So I don't think these two sessions are interesting enough. This will be interesting because it contains digital logic, truth tables. and I have to remember a lot of things here. Okay, I'll just go through this first. So this is basically, we can just break down the, it's basically a problem solving theorem that we can just break down the core problem into simpler terms, and we can just move ahead with it. Yeah, so if I'm not wrong, this is what we have to do. So every collection of six people includes a club of three people and a group of three strangers. Okay, so proof is by a case analysis. Let's X note the six people, one of six people, and there are two cases. Among five other people beside X, at least three have met X. Okay, among other five people, at least three have not met X. Um, okay, yeah, it's true. Now we have to be sure that at least one of these two cases must hold. But that's easy. If we split five people into two groups, okay. All right. So there are some cases that we can just go through. So let's say there are five people here, um, five other people beside X. So we can just split it into groups, and in case one, if the people shake hand with X, then we can say that those are the people who met X. We can just assume it because it's not something that we have to be very sure about it, but yeah, we can just assume it. So from this thing we can divide it uh, into the groups or clubs. Okay, it makes sense now. Very honestly, I'm not getting interested by these things. Yeah, it's a very true notation that proof is to establish the truth of assertion and with an absolute certainty, and we can, and in a way so that we can cross verify and or check it. So mathematically we can prove a lot of things, but humanly it's not possible to prove or make an assertion on a lot of things and calculate everything manually. Okay, let's see what's this. So, well, ordering principle. So, every non-empty set of non-negative integers has a smallest element. Okay, the statement is known as well ordering principle. Do you believe it? Seem sort of obvious, right? Yeah, but notice how tight it is. It requires a non-empty set. Okay, it's false for empty set, which has no smallest element because it has no elements at all. Okay, and it requires a set of non-negative integers. It's false for the set of negative integers and also false for the some set of non negative rationals. For example, a set of positive rationals, so that a well ordering principle captures something special about non-negative integers. While the well ordering principle may seem too obvious, it's hard to see offhand uh, why it is useful, but in fact it provides one of the most important proofs. Okay, proof rules in discrete mathematics. In this chapter we'll illustrate the power of proof method with simple examples. Okay, let's see what is this. So we actually have read well ordering principle for granted in proving uh, yeah, it's irrational. The proof assume that for positive integers m and n, the fraction this can be written in lowest term, that is in the form of m dash n dash, where m dash and n dash are positive integers with no common prime factors. Yeah, yeah. So suppose contrary, that there are positive integers m and n such that fraction of this cannot be written in lowest term. Now let's see be the set of positive integers that are numerators such as fractions. Then m belongs to c. Um, so c is not empty. Yeah, it is correct. Therefore, well ordering must be smallest integer. So m naught belongs to c. So by definition, c is an integer. So n naught is bigger than 0. Yeah, so if it's bigger than 0, then thereafter, there only, it would be a valid point. The fraction m naught by n naught cannot be written in lowest form. Okay, this means m naught must have a common prime factor. So this function is bigger than 1, but so anyway, expressing the left hand function in lowest term would also work for m naught and naught, which implies m naught by p and not by p cannot be written in lowest term either. So by definition, c, no matter m naught by p is c, but m naught by p um, is less than m naught. Is it? Yeah, it's correct. It's dividing, so it must be less than m naught, which contradicts the fact that m naught is smallest element of c. Okay, yeah, it's true. Since the assumption that C is non-empty leads to a contradiction, it follows that C must be empty. That is, that there there are no numerators of fractions that can't be written in lowest term, and hence all such fractions at all. We have been using well ordering principle on the sky from early on. Okay, it's correct. Okay, let's read this. Okay, yeah, it makes sense at this point of time. Bro, I just want to read these things. Uh, let's read, bro. Who is stopping me? No one is stopping me. Let's read. Okay, what is digital logic? Adding in binary. Yeah, binary circuit, half adder. I have to watch the video lecture of this. Yeah, we can construct De Morgan's law from the truth table. Okay, I will watch this video lecture of this thing. This seems very interesting to me. Um, no, not this one. This one. So this is the thing that I really want to study, probability, and I believe uh, this is more kind of sequence and series. Okay, two pair poker hands. From here we will watch videos too, so it would be good. Okay, I just want to finish this proofs kind of things as quickly as possible because it's not the thing that I like really. Um, yeah, I guess there were only two sections of proofs, so that was hard. Three sections of proof, so that was pain. um, let's read this. So is this proposition? Okay, I thought it was truth our truth tables. Okay, let's read see this first. What's this?
We're going to talk about propositions and logical operations in this little clip, and let's begin then with a discussion of propositions. So, to a mathematician, and in particular in this class, we're going to use the word proposition to refer to something that is either true or false. An example would be there are 5 regular solids. This happens to be true, and some terms we even prove it. It implies, for example, that if you wanted to place, let's say, 100 fixed position satellites around the Earth in a uniform way, you can't do it because there isn't any 100 vertex regular solid. The biggest one is 20 vertices. Okay, well, if I change it to 6, guess what? The assertion there are 6 regular solids is false. So that's a simple-minded example of two well-defined propositions, one of which is true, one of which is false. Propositions don't have to be true. always. What are some non-examples? Well, wake up is not a proposition because it's an imperative. It's not true or false. And where am I is a question. It's not true or false. And it's 3 p.m. is not a proposition because it's true or false at any given moment, but whether or not it's true or false depends on the time. And that's a complication we don't want to get into. The idea is a proposition is some fixed assertion that's either true forever or not true forever. Now, one of the reasons why mathematicians bring up this abstraction of propositions and the operations on them that we're about to see is that ordinary language tends to be ambiguous. And that, of course, will cause problems in mathematical reasoning just as it would in a program. One of the most ambiguous of the phrases in English that connects propositions is or. So let's look at this example. Greeks carry swords or javelins. And if I was transcribing this into precise math notation, I could say G for Greeks implies S for swords or J for javelin. So this is an assertion that if you're Greek, then you carry a sword or a javelin. Greeks implies sword or javelin. Really, I should say Greek soldiers, but
So basically, these are the same things that we have read in the PDFs and all. I will just go ahead and see if there's something else. Like I was interested to learn about truth tables. So okay, so here is truth table now. I will start from here only.
so let's be more precise about the two definitions of OR and XOR and how they work. And the assertion is that if I think of P and Q as placeholders for propositions that are either true or false, then the composite proposition, P or Q, is true if and only if P is true or Q is true or both are true. And I could express this assertion in English, this is if and only if, by giving you a so-called truth table, where in these two columns, or in all these rows, I've enumerated all the possible pairs of values of P and Q. So P and Q might both be true, that P might be true and Q false, P false, Q true, and both of them are false. And for each of those possible combinations of the truth values of P and Q, I tell you the truth value of P or Q. And the notable thing is this last row, where I'm telling you that the only way that P or Q is false is if both P and Q are false. Okay, for XOR, as we said, the P or XOR Q is true if and only if exactly one of P and Q is true. So if I was expressing that as a truth table, we'd see that where there's TT, it's false, and where there's FF, it's false, because it's not the case in either of those two rows that exactly one is true. But the middle rows, exactly one is true, and so P XOR Q is true. So this truth table is just a precise way of defining how XOR acts on truth values. There's another connective AND, which works even more straightforwardly. The value of P and Q is true if and only if both P and Q are true. And there's this truth table. Again, the salient row is that it's true only if and only if both P and Q are true. Another crucial logical operation is the negation operation, or not. So not P just flips the truth value of P. If P is true, then not P is false. If not P is true, then P is false. And there's its very trivial truth table, trivial because there's only two values to be concerned about when P is true, not P is false. When P is false, not P is true. Now, one of the places that this notion of combining basic propositions to using logical operations to build up more complicated composite propositions is in programming. Here's a typical kind of phrase that comes from Java. Java uses this double vertical bar to mean or, inclusive by the way, and double ampersand to mean and. So in Java, this is a piece of legitimate Java code that's doing a test to evaluate this expression. If x is greater than 0 or x is less than or equal to 0 and y is greater than 100, then if that test comes out to be true, then you do a bunch of code that follows the test up to some delimiter that tells you where to stop. And if it's false, you just skip all that stuff and go on. So we use sort of Boolean expressions or logical expressions like this in a very standard way in most programming languages. The other place where these operations comes up is in digital logic. And the digital circuit designers have their own notation, which I'll just mention, but we're not going to, again, impose on you, but you should be aware of. One notation they use that we'll use as well because it's so economical is that not x can be abbreviated by writing a bar over the x. More generally, not a complicated expression can be abbreviated by writing a bar over the complicated expression. That just saves some space, and so we'll use it, but not the following. In digital logic, the idea is that you're talking about circuits where the only distinction of the signal that's coming in electrically is whether it's a high voltage or a low voltage, with high voltages denoted
So probably this is the sample that we should learn, or at least remember, not learn. So give me a minute. I just need to configure a setting of OneNote so that I can take screenshots. Okay, I actually don't know which setting to go, so I have to figure out. Okay, to give the permission for screenshot, I need to uh, in OneNote I need to give the screen recording and monitoring setting to OneNote, which I'm giving in my second monitor at this point of time, and I will just take the screenshot of this thing, and yeah. So I think it's done. Yeah, I can take screenshots now. So
by 1 and low voltage denoted by 0. And the way that digital logic behaves is that the 1 corresponds to true and the 0 corresponds to false. Then the AND operation is simply multiplication because 1 or 0 times 1 or 0 is 1 only when both of them are 1 for ordinary multiplication, which is exactly the way AND behaves when 1 means true and 0 means false. Unfortunately, the digital designers use plus when they mean or. They do not mean that 1 plus 1 is 2. They mean that 1 plus 1 is 1. And just a thing to watch out for. That's part of the reason we're not going to use this notation. Let's just stick to our ordinary word notation that we give on the right.
Okay, so it wasn't that complicated, but yeah, it was simple, like the basic digital notations. um, I spent a lot of time to just figure out how to give the permission to OneNote for screenshot. So yeah, made I put this thing in the notes. All right, we can move ahead actually. Okay, it was a lot simpler to understand by lecture, but it was fun to go through all the PDFs and brainstorm the things, read the things by myself. And so we can just solve the problem set now. Okay, okay, we just finished one unit kind of thing, because this whole unit comprises of one problem set. And we can just jump to the second unit, which is quantifiers and sets. Okay, this first unit is actually quite long. After that we have okay, structures is long too, then counting probability is on a smaller term, but the content depth in probability matters a lot. So we will study probability and counting, which comprises of sequence and series. APGP, there must be APGP, yeah. So we will learn these kind of things in depth. Okay, I'm actually excited about the last two or three, last two units, because here these things are boring. But yeah, I will just try to just skim it quickly. What is GCDs and linear combinations? Okay, okay. Okay, where were we? We were at, we just finished this, and we are in this. Let's see what are this. What is this? And I will go with lecture. Lecture seems, I mean, pretty obvious and pretty good. It's only of what? Okay, okay, okay. It's not written now.
The logic of predicates is a basic concept in mathematical language, as well as being a topic on its own.
Okay, I believe I read predicate in the PDF too, if I'm not
In
wrong.
particular, I'm going to talk now about the idea of the two so-called quantifiers. For all, that's the upside down A, and exists, that's the backward E. So what's a predicate? Basically, a predicate is a proposition, except it's got variables in it. Here's an example. P of xy is the predicate that depends on x and y, and let's say it's defined to be x plus 2 equals y. Now, in order to figure out whether or not a predicate is true, I need to know the values of the variables, in this case x and y. So if I tell you that x is 1 and that y is 3, guess what? P of 1 and 3, P of x and y when x is 1 and y is 3 is true, because in fact 1 plus 2 is equal to 3. If I tell you that x is 1 and y is 4, then since 1 plus 2 is not equal to 4, P of 1 and 4 is false. On the other hand, since P of 1 and 4 is false, that makes not P of 1 and 4 true. That's the easy part. Now the quantifiers are read as for all and exists, but they control a variable. So I write for all x, it means for, it's, sorry, I write upside down ax and I read it as for all x. I'm so used to reading it that I forgot that I needed to read symbols literally. And backwards ey is read as there exists some y. So let's see how that would work. The upside down a for all acts like an and to understand what it means, let's look at this example. Let's let a variable s range over the staff members in 6042 at this term, of whom there are about 30, counting the graders. Let's define a predicate that depends on the variable s, called p of s, that says that s is pumped about 6042. They're enthusiastic about being on the staff. Okay. If I tell you for all s, p of s, that's exactly the same as saying that p of Drew is true, and p of Peter is true, and p of Keshav is true, and a whole bunch more ands down to p of Michaela. There'll be 29 ands if there are 30 staff members. Similarly, the backwards either exists acts like an or. If I tell you that t is now ranging over the 6042 staff just as s was, and I write b of t, the predicate of t that means t, the staff member t, took 6042 before, then if I tell you that there exists a t, b of t, what I'm telling you is that b of Drew, either Drew took it before, or Peter took it before, or Keshav took it before, or Michaela took it before. This statement is true because, in fact, several of the staff members took 6042 from me before. And I like to think that the previous one, that everybody's pumped up on the staff, is true, although I can't guarantee that. So let's do a little practice with existential quantifiers. So let's agree that the variables x and y will range, for this example, over the non-negative integers. And let's consider the following predicate about y that says that there's some x that's less than y. Q of y is there exists an x, that x is less than y. Let's see what happens. Well, what about Q of 3? The Q of 3 is saying that there is an x such that x is less than 3. Well, an example of such an x is 1. So that means there is an x that's less than 3 because 1 isn't. So that makes this Q true. All right. What about Q of 1? Well, again, there's an x that's a non-negative integer, namely 0, that's less than 1. And therefore, Q of 1 is true. On the other hand, Q of 0 is false because there is no non-negative integer that's less than 0. And so there's no value that you can assign to x that's a non-negative integer that will make it less than 0. Okay, that one's not so bad, I hope. Let's look at the same example with a universal quantifier. This time we'll say that r of y means that for every x, x is less than y. Well, r of 1 is false, and the reason is that 5 is a counterexample. 5 is not less than 1, and so it's not true that every x is less than 1. R of 8 is false because 12 is not less than 8, and therefore not every x is less than 8. R of a googol, 10 to the 100th, is false because if you let x be a googol, it's not less than a googol, and so it's an example of the fact that this doesn't hold for all x's. That part's obvious. Okay. The thing that tends to confuse people in the beginning is what happens when you start mixing up quantifiers. So let's look at an intuitive example first that might help you remember what happens when you have an A followed by an E, and then we'll look at an E followed by an A. So suppose I look at this statement. This time I'm going to tell you that V ranges over the possible computer viruses, not biological viruses. D ranges over antivirus software, defenses against viruses. And I want to look at the predicate that says for every virus, there is a defense such that D protects against V. This defense is good against that virus. All right. So Each virus I have a defense for. So an example would be, these are, by the way, dated viruses, but that's when the slides were made. So against the MyDoom virus, you could use Defender, a Microsoft Defender. Against the I Love You virus, you could use Norton. Against the Bobless virus, you could use Zone Alarm. Well, is that what we want? It's expensive. It means that for every different virus, I need a different defense. I have to spend a fortune on software. This is not what we want. So that's when for every virus there's a defense, but the quantifiers are in the wrong order. Let's reverse them. Suppose I tell you that there's one defense that's good for all viruses. There is a defense such that for every virus, D protects against V. For example, if D is MIT virus scan, then it would be wonderful it was true that D protects against all viruses. There's one defense good against every attack. That's what we want because it's a lot cheaper. All right, let's start looking at a concrete mathematical example that, and I hope that prelude with the viruses will help you decipher how the quantifiers behave. So let's look at this predicate now. This is a proposition. It really doesn't depend on the values of x and y. It's asking about all possible x's and all possible y's, whether there is one. In order to figure out whether a proposition like G is true, actually, I do need to know what x and y are ranging over, because as you'll see, whether or not G comes out to be true will depend on that. So I'm going to look at the domain of discourse.
So basically, in quantifiers, we need the value of the terms to basically describe the whole thing. So everything depends on each other. So even after getting the value, after getting the value, we can just define it as if it's true or false. So that's all we can do, and that's what quantifiers classifies as. Yeah, for different values there should be different uh, for different value of the domain there should be different values for Z. For some it would be true, for some it would be false. Yeah, it makes total sense. uh, Reverse the quantifiers. Okay, what's this here? So this means exist here for all numbers for domain, and H is F, H is false. um okay, yeah, there's no bigger non-negative integers, so yeah, that's why it's false. Okay, it makes sense. For this there's -1, that's why it's true. Okay, okay, we finally reached something where we can solve some maths. I was very excited. I'm very excited to solve some maths. Let me once see if my stream is running out or not. Yeah, so this is of which one? um in class sessions we had We have PDF of this. Okay, let's see the lecture first. Okay, I don't know why it's not loading, but it should load because everything is working fine from my side. Internet is good. I don't know why it's not loading. We can read the um, PDF in the meantime. Okay, let's do it quickly because set is something which is on the easier side. Yeah, this is how we write sets in the curvy bracket. Okay, some popular sets. This is a null set, empty set. You can call it a null set too. This is for non-negative. This is for integers. It's used for rationals. It's for real number, complex number. Okay, compare and combining sets. So it's going to combine set. For example, suppose this is x, this is y. The union of set A and B denote this includes exactly elements appearing for in the both set. So uh, by unioning, we can just take the values inside the set which shouldn't be repeating like this. Okay, so here by intersection we can only take the numbers or values, or you can say elements, which are in both of the sets. Okay, so if we do x minus 5, then we get 2 and 3 is here, 2 and 3 is here, so difference is, this is a difference, 1 and 4. So x minus y is 1 and y minus x is 4. X minus 5 is 1, 1 is here, and y minus x is 4. Like 4 is the only difference here. Okay. So we have to remember that this is complement of A, so that if A is a null set, um, A the complement of this is a null set if and only if A equals to D. Yeah, if the both are equal, then their complement would be null set 0. The set of all subsets in the set A is called a power set. Power of A is okay. So B belongs to the power set of A if and only if uh, B belongs to A. Okay, this is a sample for equivalence. Okay, this is important. If A has n elements, then there are uh, 2n sets in the power. Okay. So if we take 1 here, then it would be 5, and if we are taking n is a prime, then 3. So 12, 1, 13. Yeah, it makes sense. The elements make sense. Proving set equalities. Okay, then yeah, distributive law, commutative law, these things will be there. Okay. Okay, then sequences. This is important. Okay, it makes total sense. So I read all of this. So it is basically that uh, here we can change the sequence, or we do have some different sets with different sequential elements, but this will be the same set, so there won't be much difference. Okay, there must be a problem from MIT side, so that's why it's not loading, because from my side it's fine.
We're going to look at the most fundamental of all mathematical data types, namely sets. And let's begin with the definitions. Really, it might help a little bit. Examples. Down. Let's look at this set of 4 things. Namely, it's got 2 numbers, pi over 2 and 7. Don't worry. There is no quickly get out of hand, is that an element is either in a set or not in a set. Like, so if I write down 7 pi over 2, 7, this is the same a description of the same set that 7 pi over 2. I'm just telling you the same thing twice here, that 7 is in the set and the 7 is in the set again. So no notion of being in the set more than once. Now, sometimes fundamental feature of a set is what's in it, and epsilon symbol. 14 over 2 is also a member of that set because 14 over 2 is just another description of 7. When I write 7 here, I don't mean not a member of. And membership is so basic that there's a lot of different ways to say it. Besides using the membership symbol, X is a member of A, you can sometimes say X is an element of A. 2/3 is not a member of the integers because it's a fraction. That's not an integer. And the membership is another fundamental notion of subset. So A is a subset of B. It's pronounced. So that horizontal U with a line under it is meant.
Okay, so this symbol came across just 5 minutes back, and I just thought it was the sign for equivalence, but I was wrong. It is for subset. I'm dumb, but yeah, I got to learn.
To resemble a less than or equal to symbol. So you can think of it as being A is less than or equal to B, but don't overload the symbols. Less than or equal to is used on numbers and other things that we know how to order, and this is a relation that's only allowed between sets. So A is a subset of B. A synonym is that A is contained in B. Simply means that every element of A is also an element of B. And if I wrote that out in predicate logic notation as a predicate formula, I'd say for every X, X is in A implies X is in B. If it's in A, then it's in B. Everything in A is in B. So some examples of the subset relation are that the integers are an integer is a special case of a real number. So the set of integers is a subset of the real numbers. A real number is a special case of a complex number, so the real numbers are a subset of the complex numbers. And here's a concrete example where I have a set of three things, 5, 7, and 3, and this is the set with just the element 3 in it. Now, we sometimes are sloppy about distinguishing the element 3 from the set that consisting of just 3 as its only element, but in fact it's a pretty important distinction to keep track of. In this case, 3 is not a subset of this set on the right, but the set consisting of 3 is a subset of the set on the right, because after all, the only member of this set is 3, and that is a member of this set. A consequence of this general definition is that every set is a subset of itself, because everything in A is in A. That's not really very interesting. Another important general observation is that the empty set is a subset of everything. The empty set is a subset of every set. Let's look at why that is in more detail. So the claim is that the empty set is a subset of everything. Let B be any old set. Then the empty set is a subset of B. What exactly does it set? Then it implies that it's in B. For every element, if it's in the empty set, then it's in B. Well, what do we know about this? The assertion that X is in the empty set is false. No matter what X is, there's nothing in the empty set. And now I have an implication, and implies where the left-hand side, the hypothesis, is false. That means that the whole implication is true, and it doesn't depend on what B is. I'm not even going to look at B. I can see that X is in empty set is false, so the whole true has to be true. That convention just lists the elements, and as we did with that set with 7 and pi over 2 and Albert R. Sometimes we can even describe infinite sets as some kind of a list, like I might describe the set of integers as saying, well, it's 0, 1, minus 1, 2, minus 2, and so on, and you'd understand that. But in general, if I'm describing a set that is not so easy to list, say the real numbers, then what I'm going to do is define a set by a defining property of in the set. So I'm interested in a property P of elements, and I'm going to look at the set of elements X that are in some set A such that P of X is true, and that's the notation we use. So
Okay, I don't know I spoke it or not because my mic was off, but I spoke it, but I don't know if my captured it not. So basically, I was just telling around about the empty set. So empty sets is in every is the subset of in the every set, but nothing is actually inside the empty set. That's what I was telling.
This would be read as the set of X in A such that P of X holds, that X has property P. So notice this vertical bar is read as such that. It's just a mathematical abbreviation. This is those elements in A that have property P, that P of X holds for. That defines a set of those elements. Let's look at a simple example. The set E of even integers is simply the set of numbers n that are integers such that n is even. So in this case, the property P of n means that n is even. One last concept is the concept of the power set. So the power set of a set A is all of the subsets of A. So we could define it using set notation as it's the set of B such that B is a subset of A. An example would be, let's take the power set of the two Boolean values, true and false. So the power set of true and false, of that set consisting of two elements is, well, what are some of its subsets? The set consisting of just true is a subset of true, false. So is the set consisting of false. And so is the whole thing. It's a subset of itself. And one final element, the empty set, is a subset of the set of Boolean values, true and false. So the power set of this two element set is a set that has four things in it, two elements of size 1, one element of size 2, one element of size 0. And that's going to be a general phenomenon that we'll examine more later. How big is the power set of a set? The even numbers, E, that we just defined on the previous slide, is a member of the power set of Z because it's a subset of integers. Even integers are a special case of integers. And the integers are a member of the power set of R. This is just a synonym for saying that integers are a subset of reals. Every integer is a real, so the integers are a subset of reals, which means they're a member of the power set of reals. So the general property is that a set B is a member of the power set of A if and only if B is a subset of A. That was the defining condition for power set. And that's a fact to remember, and it may potentially confuse you, but it's a good exercise to
So B belongs to a power set of A if and only if B belongs to A. If and only if B is a subset of A. Yeah, it makes sense. It makes sense. Okay. It actually makes sense. So we just finished sets. Were there some class questions? I don't think so. Let's see. Okay. Okay, so this is the same thing, I mean, which we just did. We need to brainstorm and revise the whole thing again and again. So I will revise this till sets, and yeah, till sets I will revise these two things or these three things which are important again in the evening session. So yeah, so I have to revise evening session till sets and solve the problem sets. Okay. Yeah, so that's my plan to do. So we finished half of this. I have to revise these things, and then I just have to revise the problem set of the uh, problem set and the whole proposition and set kind of things with theory. Okay, I will just do that in the next session whenever I just come to study. So that's the whole plan. All right.